deep in the endless night, a colossal force 4 million times heavier than our sun swallows light and bends reality itself. This unseen behemoth commands the swirling dance of 400 billion stars at our galaxy's core. Witness a realm where time crawls to a halt, space twists like molten glass, and a lone star races at 17 million miles per hour to evade oblivion. Delve into the universe's most profound physics, where gravity's unyielding grip unveils secrets that redefine existence. For more explorations into these cosmic depths, subscribe to Cosmic Depth. The heart of the galaxy pulses with raw power and enigma. Prepare yourselves. We begin. From the quiet of our night skies, the stars appear scattered and still, but they follow an unseen rhythm across the Milky Way. Our galaxy, a vast spiral of 400 billion stars, gas clouds, and dark matter, rotates with precision around a central point. The solar system itself hurtles at 515,000 miles per hour in a 240 million year orbit, a path unchanged since dinosaurs walked Earth. Yet, this motion defies simple explanations. Early astronomers thought stellar gravity alone held it together, like a cosmic ballet where each star pulls on its neighbors. But measurements told a different story. Stars at the galaxy's edge race too fast, defying escape into the void. Visible matter couldn't account for this grip. Something massive, hidden at the center, must anchor it all. Millions of solar masses in a tiny space. Through dust veils in Sagittarius, telescopes glimpsed hints of this force, a gravitational giant shaping the galaxy's form. What lurks there, commanding such power? The mystery of this invisible anchor draws us closer. The discrepancy grew clear. Orbital velocities demand extra mass. Stars orbit faster than visible light suggests, implying an unseen force. In the 1930s, Fritz Zwicky noted this in galaxy clusters, coining dark matter. But the Milky Way's core held a concentrated puzzle. Radio waves pierced the dust, revealing Sagittarius as a star in 1974, a bright source outshining stars, yet invisible in light. This compact emitter, smaller than our solar system, packs energy rivaling billions of suns. No ordinary star or cluster could fit. It must be dense beyond imagination. Gravitational calculations confirm 4.3 million solar masses in a space tinier than Mercury's orbit. Pack that much matter, and normal physics collapses. The galaxy's spiral arms, our solar system's path, all tied to this hidden titan. As observations sharpened, the evidence mounted. Something warps space-time itself, holding the Milky Way intact. But to unmask it, we turn to the tools that see beyond the veil. This anchor's influence extends far, gripping stars 26,000 light-years away. Yet, its heart remains shrouded in dust, blocking visible light. Infrared glimpses show chaotic motion near the center, stars defying norms. The Event Horizon Telescope's 2022 image later confirmed the shadow, but early clues came from orbital math, discrepancies proving a supermassive core. Without it, the galaxy would unravel, stars flung into intergalactic space. This invisible force shapes our cosmic home, a predator at the heart. As we probe deeper, radio signals emerge as the key, whispering from the darkness. What form does this monster take, and how does it reveal itself through waves that cut through the fog? The path to unveiling Sagittarius A leads us into the realm of unseen light. The invisible anchor grips our galaxy, but its heart lies cloaked in cosmic fog. Thick dust clouds in Sagittarius, 26,000 light-years away, block visible light, hiding the Milky Way's core from early telescopes. Stars and gas swirl around an unseen force, yet optical lenses saw only darkness, like a city lost in a sandstorm. In the 1950s, astronomers turned to radio waves, which slice through dust like a blade through mist. By 1974, Bruce Ballack and Robert Brown aimed the Green Bank telescope at the galactic center, expecting faint stellar hums. Instead, a brilliant radio beacon blazed, brighter than any star cluster, confined to a region smaller than our solar system. They named it Sagittarius, a star, the asterisk marking its enigma. This wasn't the scattered glow of gas or stars. It was a pinpoint of raw energy. The discovery hinted at a massive, compact source, but what could shine so fiercely yet remain invisible? The dust veil was parting, revealing a cosmic secret. Radio waves unveiled what light could not, but the puzzle deepened. Sagittarius A star signal, detected in 1974, was no ordinary emission. Unlike flickering pulsars or diffuse gas clouds, its steady, intense radio output suggested a stable, massive object. 4 million solar masses, calculations later showed. Visible light telescopes, blinded by dust, saw nothing, but radioscopes, like the Very Large Array, mapped a compact source, just 12 million miles wide. Infrared observations, piercing dust in the 1990s with the Keck telescope, revealed stars orbiting this void at breakneck speeds. These glimpses confirmed a gravitational giant, yet its form remained elusive. Was it a dense star cluster? A neutron star? The radio signature hinted at something denser, its energy dwarfing entire stellar populations. Speculation stirred. Could this be a black hole, warping space itself? Astronomers needed more than waves. They needed to see the orbits of stars caught in its grip to confirm the truth. Imagine a curtain of dust parting to reveal a cosmic stage. By the 1980s, radio telescopes like Effelsberg refined Sagittarius profile, a point-like source with magnetic fields twisting in patterns no star could mimic. Infrared breakthroughs using adaptive optics on Keck and VLT showed stars racing around an empty point, hinting at a mass too vast for normal matter. The dust, thick as a galactic fog, scattered visible light, but infrared and radio cut through, exposing a region where gravity ruled supreme. The 2022 Event Horizon telescope image would later confirm a black hole, but these early glimpses, radio beacons, orbiting stars, laid the foundation. Why was Sagittarius so shy, hiding behind dust, yet screaming in radio waves? Some, like Avi Loeb, mused, does its signal carry intent? Science pointed to a natural beast, but the veil's parting raised questions. What forces shape this monster's dance with the stars? The cosmic stage sets for their orbits. As the dust veil parted, a cosmic signal roared from the galaxy's heart. In 1974, astronomers Bruce Ballack and Robert Brown, wielding the Green Bank telescope, uncovered a blazing radio source in Sagittarius A star. Unlike the faint hum of stars or gas, this was a concentrated beacon, outshining entire stellar clusters, yet confined to a space smaller than our solar system. Named for its constellation, this point glowed with energy rivaling 1 billion suns, steady and unyielding. Radio waves, slicing through the dust that blinded optical scopes, revealed a source just 12 million miles wide, emitting a symphony of magnetic fields and plasma. This wasn't a star's gentle glow or a nebulous diffuse haze. It was a cosmic lighthouse pulsing with power. Early theories faltered. No star cluster could be so compact, no gas cloud so intense. What fueled this relentless signal, invisible to all but radio eyes? The beacon's voice hinted at a monster, but its true form remained cloaked. The radio beacon of Sagittarius A star burned with clues no other wavelength could offer. By the 1980s, the Very Large Array sharpened the picture. A point-like source, radiating steadily for decades, unlike flickering pulsars or variable quasars. Its energy output, equivalent to our sun's yearly production in a single second, demanded a mass of 4 million suns squeezed impossibly tight. Radio observations revealed structured emissions, with magnetic fields twisting like cosmic vines, suggesting rotation and intense gravity. Unlike stars, which shine across spectra, or nebulae, which scatter light, this signal was pure, focused, and relentless. Astronomers puzzled. A neutron star was too small, a cluster too chaotic. The stability hinted at a single, massive object, perhaps a black hole swallowing matter. Avi Loeb's later musings stirred speculation. Could such a signal be artificial, a galactic marker? Science leaned toward natural plasma flows, but the beacon's clarity nagged. Why broadcast so powerfully in radio alone? The signal pointed to a force shaping the galaxy's core. Envision a cosmic orchestra, with Sagittarius A star as its conductor, its radio waves a melody piercing the void. By the 1990s, telescopes like Effelsberg and Nobayama mapped intricate patterns, spirals of plasma, magnetic loops, within a region no wider than Mercury's orbit. This beacon, emitted since its 1974 discovery, held steady, its power dwarfing nearby stars. The signal structure, seen in 2025 ALMA data, suggested matter spiraling toward a gravitational abyss, heated to millions of degrees. No ordinary object could sustain such intensity without collapsing. The radio waves, unlike scattered starlight, pointed to a single source, dense and inescapable. Scientists saw a black hole's accretion disk glowing as matter fell. Yet, some, like Loeb, wondered, could this precision signal intent, a cosmic flare for distant eyes? As radioscopes refined the view, the beacon's energy framed a monster. How does this force pull stars into its frantic dance? The cosmic melody leads us to their orbits. The radio beacon of Sagittarius A star sings a cosmic melody, but its true power shines in the frantic dance of nearby stars. In the 1990s, infrared telescopes like Keck pierced the galactic dust, revealing a cluster of stars orbiting an unseen point at unimaginable speeds. Unlike the gentle drift of most stars, these moved like racers on a cosmic track, defying normal stellar motion. The star S2, a blue giant, became the standout, completing a 16-year elliptical orbit around nothing visible. At its closest approach, just 120 astronomical units from the center, S2 hit 17 million miles per hour, fast enough to cross Earth in seconds. This isn't a leisurely waltz, it's a desperate sprint under crushing gravity. Such orbits demand a mass of 4.3 million suns packed into a space smaller than our solar system. No star cluster could hold so tight. What force choreographs this dance, pulling stars into such extreme paths? The stellar races begin to reveal the monster's grip. S2's orbit is a cosmic laboratory, testing physics at its limits. In 2018, during its closest approach, VLT measurements clocked it at 7,650 kilometers per second, 5% of light speed. Its path, stretching from 970 to 120 astronomical units, traces an ellipse so sharp it defies stellar norms. Other stars, like S4714, swoop even closer, within 12.6 astronomical units, reaching speeds that blur the line between matter and light. These orbits, mapped by UCLA's Galactic Center Group, show a single, massive object anchoring them, Sagittarius A. A cluster would scatter their paths chaotically, but these remain fixed, like planets around a sun. The gravitational pull warps space, bending starlight into redshifts, as Einstein predicted. Such precision points to a black hole, not a star or nebula. Yet, the dance feels almost staged. Could these stars, as Avi Loeb might muse, orbit a cosmic signal, meant to draw our gaze? Science sees gravity's work, but the choreography sparks wonder. How does this monster weigh so much in so little space? Picture stars caught in a gravitational storm, their orbits a testament to an unseen titan. S2 and its companions, tracked by ESO's gravity instrument, reveal a center so dense it defies normal matter. If 4.3 million suns filled that space, they'd collapse or explode. Yet, these stars survive, their paths stable despite tidal forces that could shred lesser objects. S4714EES 2025. Data shows it grazing just beyond the event horizon, its speed pushing relativistic limits. These orbits, unlike our solar system's calm circles, are elongated, frantic, a dance choreographed by a force bending space-time. The precision of their paths, unmoved by nearby stars, confirms a single, compact monster, Sagittarius A. Scientists see a black hole's signature, but the spectacle invites questions. Why do these stars dance so perfectly for our telescopes? Loeb's whispers linger. A natural trap or a cosmic stage? The orbits lead us to measure the beast's true mass. The star's frantic dance around Sagittarius A star unveils a cosmic scale, measuring a monster hidden in plain sight. The orbits of S2 and its companions, racing at millions of miles per hour, trace the gravitational grip of an unseen giant. By the 1990s, astronomers realized these paths held the key to weighing the galactic core. Newton's laws, refined by Einstein, turn orbits into precise scales. The tighter and faster the orbit, the heavier the central mass. S2, looping every 16 years, reaches 17 million miles per hour at 120 astronomical units from the center. This speed demands a colossal force, millions of suns worth, packed into a space no wider than Mercury's orbit. Early calculations, using Keck telescope data, pegged Sagittarius A at 4.3 million solar masses, a number too vast for stars or gas clouds. Such density defies normal matter. What could anchor such weight in so small a space? The cosmic scales begin to balance, revealing a behemoth's true measure. S2's orbit is a cosmic equation, solving for the mass of Sagittarius A. In 2018, ESO's gravity instrument tracked S2's closest approach, 120 astronomical units, at 7,650 kilometers per second, 5% of light speed. This elliptical path, stretching to 970 astronomical units, yields precise math: 4,297,000 solar masses, accurate within 12,000. No cluster could fit. Stars would collide or scatter. A neutron star falls short by orders of magnitude. Only a supermassive black hole matches, compressing unimaginable mass into a pinpoint. Other stars, like S4714, swooping within 12.6 astronomical units, confirm this, their orbits stable despite crushing gravity. The math is unyielding, as Newton and Einstein foretold. Yet, the precision nags. Why so perfect for our telescopes? Avi Loeb muses, could this be a staged signal meant to be measured? Scientists see natural orbits, but the weight, 4.3 million suns in a space smaller than our solar system, defies intuition. The scales tip toward a singular truth, but questions linger. Picture a cosmic balance weighing a monster that warps reality itself. S2's 16-year orbit, refined by 2025 VLT data, locks Sagittarius A's mass at 4.3 million suns, with orbits like S4714S tightening the figure. This precision comes from centuries of physics, Kepler's laws, Einstein's relativity, applied to stars racing around an empty point. If normal matter filled this space, it would erupt in cataclysmic fusion. The density, approaching infinity, points to a black hole where matter collapses beyond comprehension. Yet, the star's paths are so clear, almost curated for our gaze. Could this clarity, as Loeb suggests, hint at a cosmic design? Science insists on gravity's work, but the mass's concentration in a 12 million mile span challenges reason. As we weigh this beast, its influence grows clearer, shaping not just orbits, but the galaxy's fate. How does its shadow appear, confirming its nature? The cosmic scales lead us to a historic image. The cosmic scales weighed Sagittarius A at 4.3 million suns, but seeing its shadow demanded a leap beyond orbits. In 2022, the Event Horizon Telescope unveiled a historic image, a glowing ring around a dark void, the first glimpse of our galaxy's black hole. Black holes trap light, making them invisible, yet matter spiraling inward heats to billions of degrees, forming an accretion disk that glows like a cosmic halo. The EHT, linking 8 radio observatories across 4 continents, created a virtual telescope the size of Earth, capable of resolving an orange on the Moon. Imaging Sagittarius A, just 12 million miles wide, was a monumental challenge. Unlike Messier 87's larger black hole, Escaray's small size and our view through 26,000 light-years of dust and gas blurred the signal. Years of data, processed by supercomputers, revealed a faint orange ring encircling a black core. What did this shadow mean for the monster's true nature? The cosmic lens begins to focus. The 2022 image of Sagittarius A was no mere snapshot. It confirmed Einstein's predictions. The dark shadow, the event horizon, marks where light vanishes, space-time curving beyond escape. The glowing ring, plasma at 10 billion degrees, spirals clockwise, its bright spots racing near light speed, twisted by magnetic fields. Capturing this required overcoming cosmic fog, dust scattering light across 26,000 light-years. The EHT's 2017 observations, processed over 5 years, filtered noise to reveal a structure matching relativity's math. Unlike Messier 87's 6 billion solar mass giant, SGRA's 4.3 million suns fit in a 12 million mile span, making its image harder to resolve. The ring's clarity stunned scientists, proving a black hole's existence at our galaxy's heart. Yet, its precision sparked questions. Avi Loeb mused, Could such a clear signal be more than natural? Science saw a disk of falling matter, but the image's perfection hinted at cosmic intent. What secrets does this glowing boundary hold? The shadow's truth deepens the enigma. Picture a cosmic portrait painted in radio waves, revealing the edge of oblivion. The EHT's 2022 image of Sagittarius E showed a shadow 12 million miles wide, surrounded by a fiery ring of superheated plasma. This boundary, the event horizon, is where space-time collapses, trapping all within. The ring's rotation, mapped by 2025 ALMA updates, confirmed the black hole's spin, its magnetic fields sculpting arcs of light. The image's clarity, despite galactic dust, was a triumph. Years of data from Hawaii to Antarctica, stitched by algorithms, matched Einstein's equations to near perfection. Yet, the shadow's stark outline raised whispers. Why so vivid for our telescopes? Loeb speculated, a natural phenomenon, or a beacon meant to be seen. Scientists saw proof of a black hole shaping the Milky Way, but the image's timing, our first clear view, felt almost staged. As we stare into this abyss, what forces test the stars daring to approach it? The cosmic portrait leads us to their relativistic extremes. The glowing shadow of Sagittarius revealed a black hole's edge, but its true power warps the very fabric of reality. Near this cosmic monster, stars like S2 race at speeds that push physics to its limits, bending light and time itself. In 2018, S2 reached 17 million miles per hour, 7,650 kilometers per second, during its closest approach, just 120 astronomical units from the event horizon. That's 5% of light speed, fast enough to circle Earth in a heartbeat. Such velocities, tracked by ESO's gravity instrument, create relativistic effects predicted by Einstein. Light from S2 redshifts, its wavelengths stretching as it climbs out of the black hole's gravitational well, losing energy. This isn't just motion. It's a cosmic racetrack where space-time curves under 4.3 million solar masses. What happens to stars caught in such extremes? The laws of relativity begin to twist, unveiling the monster's deeper influence. S2's sprint around Sagittarius A is more than speed. It's a test of Einstein's universe. At 120 astronomical units, S2 feels gravity so intense that space-time warps, stretching light and slowing time. In 2018, VLT observations caught a 200 km per second redshift in S2's light, a blend of gravitational and Doppler effects. Photons fight to escape the black hole's pull, reddening as they climb, just as relativity predicts. Other stars, like S4714, graze closer at 12.6 astronomical units, hitting speeds near 8% of light speed. These velocities, mapped by UCLA's Galactic Center group, confirm a mass so dense, 4.3 million suns, that normal matter would collapse. The orbits remain stable, defying tidal chaos. Could this precision, as Avi Loeb might hint, suggest a cosmic stage designed to showcase such extremes? Science sees gravity's work, but the clarity of these effects, perfectly measurable, sparks wonder. How does time itself bend under such forces? The relativistic extremes push us toward a deeper truth. Picture a star racing where physics phrase, its light and time warped by a cosmic titan. S2's 16-year orbit around Sagittarius A, refined by 2025 gravity data, shows relativistic effects in stark clarity. At closest approach, its redshift stretches light by 200 kilometers per second. a sign of spacetime's curvature under 4.3 million solar masses. Time itself slows for S2, clocks on the star lag by fractions of a second compared to Earth, a measurable dilation Einstein foresaw. S4714, dive in closer, endures even wilder extremes, its speed pushing the limits of matter's survival. These stars, orbiting a 12 million mile wide void, reveal a black hole's grip, bending reality itself. The precision of these measurements, seen through our telescopes, feels almost too perfect. Loeb's speculation lingers. A natural phenomenon or a cosmic signal? Scientists affirm relativity's triumph, but the extremes invite questions. What forces allow stars to endure such strain? The cosmic racetrack leads us to time's own distortion. The relativistic extremes of stars racing around Sagittarius bend light and speed, but they also twist something deeper: time itself. Einstein's general relativity predicts that intense gravity slows time's flow, a phenomenon starkly real near the galaxy's heart. S2, hurtling at 17 million miles per hour, just 120 astronomical units from Sagittarius A, experiences this warp. In 2018, ESO's gravity instrument measured S2's orbit, revealing time dilation as clocks on the star tick slower than those on Earth. Near 4.3 million solar masses, space-time curves so steeply that seconds stretch, as if caught in a cosmic tide. This isn't science fiction, it's measurable physics, seen in the redshift of S2's light. What does it mean to exist where time lags behind the universe? The cosmic clocks begin to falter, unveiling a black hole's profound grip. S2's orbit is a laboratory where time bends under Sagittarius A's weight. At its 2018 closest approach, 120 astronomical units from the event horizon, S2's clocks lost fractions of a second compared to Earth. Time dilation made real. For every million seconds here, S2 experiences roughly 999,999, a subtle but measurable lag. S4714, diving closer at 12.6 astronomical units, faces even stronger effects. Its time slowed further by gravity's crush. VLT and Keck data from 2025 confirm these shifts, matching Einstein's equations with eerie precision. The black hole's 4.3 million solar masses warp spacetime like a river caught in a vortex, slowing its flow. If you stood on S2, your heartbeat, your thoughts would align with this slower rhythm, unnoticed by you but clear to distant observers. Could this warp, as Avi Loeb might ponder, signal a cosmic design? Science sees gravity's natural pull, but the effect's clarity sparks curiosity. How does time's distortion shape the star's survival? Picture time as a river, its flow warped near Sagittarius A's crushing mass. S2, racing at 5% of light speed, sees time slow by fractions of a second, a dilation confirmed by 2025 GRAVATY measurements. S4714, grazing the event horizon at 12.6 astronomical units, endures even greater distortion, its clocks lagging more as gravity intensifies. This isn't mere theory. Photons from these stars redshift, losing energy as they climb the black hole's gravitational well, a clock slowing in sync. The 12 million mile wide monster, packing 4.3 million suns, creates a space-time bend where seconds stretch into eternity. Such precision feels almost orchestrated, prompting whispers like Loeb's. Is this a natural quirk, or a stage for cosmic observers? Scientists affirm relativity's triumph, but the warped time raises questions. How do stars endure such a twisted reality without breaking? The cosmic river leads us to their battle against tidal forces. Time warps near Sagittarius A, but the stars dancing in its grip face another trial: tidal forces that could tear them apart. At 120 astronomical units, S2 races at 17 million miles per hour, enduring gravity's brutal pull from 4.3 million solar masses. Tidal forces, stronger on the star's near side than its far, stretch it like dough in a cosmic storm. Most objects would shred under such strain, yet S2 survives, completing its 16-year orbit intact. Closer still, S4714 dives within 12.6 astronomical units, where tidal forces intensify, threatening to rip matter apart. These stars, observed by ESO's gravity, defy destruction despite a black hole's wrath. Their resilience hints at immense density and mass, but how do they hold together? The cosmic storm tests their limits, revealing the monster's relentless power. S2's survival is a marvel of physics. At its 2018 closest approach, 120 astronomical units from Sagittarius A, tidal forces pull its near side with billions of times Earth's gravity, while the far side feels less. This gradient could fracture a planet, yet S2, a blue giant, holds firm. Its mass, 15 times our Sun's, and dense core resist the stretch. S4714, grazing at 12.6 astronomical units, faces even fiercer forces. Its speed, near 8% of light speed, amplifying the strain. VLT data from 2025 shows both stars' orbits stable, their surfaces glowing despite tidal stress. Normal matter would vaporize, but these stars' density defies the black hole's grip. Could their endurance, as Avi Loeb might speculate, suggest a cosmic anomaly, crafted to withstand such extremes? Science points to stellar evolution, but their survival feels almost defiant. How do they endure forces that warp space-time itself? The cosmic crucible reveals their strength. Picture stars battling a gravitational tempest, their survival a testament to cosmic resilience. S2 and S4714, orbiting Sagittarius A's 4.3 million solar masses, face tidal forces that stretch their cores like taffy pulled by a giant. At 12.6 astronomical units, S4714 endures gradients that could shred moons, yet its orbit, mapped by UCLA's Galactic Center Group, remains steady. S2, at 120 astronomical units, resists forces billions of times stronger than Earth's tides. Their density, forged in stellar nurseries, holds them together, as 2025 Keck data confirms. These stars' surfaces blaze, unyielding, despite gravity's crush. The black hole's event horizon, just 12 million miles wide, looms close, yet they persist. Loeb's whispers linger. Is their survival natural or a cosmic design? Scientists see dense stars defying physics, but their endurance sparks wonder. What fuels this monster, driving such forces? The cosmic tempest leads us to its feeding ground. Stars survive the tidal wrath of Sagittarius A, but the black hole's hunger drives a different spectacle. This cosmic beast, 4.3 million times our Sun's mass, feeds on matter drawn into its gravitational maw. Gas, dust, and stellar debris spiral inward, forming an accretion disk that glows with ferocious heat. Unlike Messier 87's blazing disk, Sagittarius A's is faint, starved by sparse surroundings, yet it flares dramatically. Chandra X-ray Observatory caught bursts in 2019, spiking 75 times brighter than usual as clumps of gas fell past the event horizon. These flares, seen again in 2025 ALMA data, light up the 12 million mile wide core, revealing a chaotic feast. The disk, a swirling vortex of plasma, heats to billions of degrees, radiating energy that outshines nearby stars. What fuels these sudden outbursts, and how does this monster sustain itself? The cosmic furnace begins to blaze, exposing its appetite. Sagittarius A's feeding is a delicate dance of scarcity and violence. Its accretion disk, thin compared to active galactic nuclei, forms from wisps of gas and stellar winds, drawn by 4.3 million solar masses. EHT's 2022 image showed a faint ring, but 2025 Chandra observations reveal flares when matter plunges inward, heating to 10 billion degrees. These bursts, lasting hours, emit X-rays and radio waves, signaling a chaotic disk twisted by magnetic fields. Unlike steady-feeding quasars, SGRA starves, consuming less than a moon's mass yearly. Yet, a single gas clump can spark a flare 100 times brighter, as seen in 2023 VLT data. This erratic hunger puzzles astronomers. Why so sparse, yet so explosive? Avi Loeb speculates, could these flares be signals, timed for our gaze? Science points to random infall, but their brilliance feels almost choreographed. How does such a faint disk drive such power? The cosmic feast reveals the black hole's restless nature. Picture a cosmic predator, its hunger lighting the galactic core. Sagittarius A's accretion disk, a faint spiral of gas and dust, feeds its 4.3 million solar masses in fits and starts. ALMA's 2025 data shows flares erupting when debris crosses the event horizon, igniting X-ray bursts that outshine the sun for hours. Magnetic fields, twisting like cosmic ropes, channel plasma into bright spots racing near light speed, as EHT images confirm. This disk, just 12 million miles wide, consumes little, less than 0.01% of Earth's mass yearly, yet its flares rival stellar clusters. The sparsity puzzles. Why does such a massive black hole feed so lightly? Loeb's musings linger. Are these bursts natural, or a beacon for distant eyes? Scientists see turbulent infall, but the timing, flares peaking as our telescopes advance, sparks wonder. What role does this feast play in the galaxy's life? The cosmic furnace leads us to its ancient influence. The cosmic furnace of Sagittarius A consumes matter in fleeting bursts, but its influence stretches far beyond its fiery meals. This black hole, 4.3 million times our Sun's mass, has sculpted the Milky Way's evolution for billions of years. Anchoring 400 billion stars, it sits at the galaxy's heart, its gravity weaving the spiral arms we call home. Simulations from 2025, using ALMA and Chandra data, suggest SGRA formed early, within the Milky Way's first billion years, as gas clouds collapsed under their own weight. Its growth shaped the galactic core, drawing stars and gas into dense clusters. Flares, like those seen in 2023, seeded the center with heavy elements, forging new stars. This monster isn't just a predator, it's a cosmic architect. How did its pull craft our galaxy's form? The tapestry of the Milky Way begins to unravel, Sagittarius A's role in galactic evolution is etched in the Milky Way's structure. Its 4.3 million solar masses, compact within a 12 million mile core, stabilized the galactic center, preventing chaotic collapse. Simulations from Harvard in 2025 show it grew by swallowing gas and stars. Its accretion disks flares, enriching the core with metals like iron and silicon. These outbursts, seen by Chandra, fueled star formation, birthing dense clusters near S-Gray. Its gravity anchored the bar-shaped core, shaping the spiral arms over 10 billion years. Unlike active galactic nuclei, S-Gray's quiet feeding suggests a balanced influence, preserving the galaxy's form. Could its restraint, as Avi Loeb might ponder, hint at a cosmic design guiding evolution? Science sees a natural engine, but its subtle power, sculpting a galaxy while barely feeding, intrigues. How does this balance shape our cosmic home? The black hole's legacy weaves deeper. Picture a cosmic loom, with Sagittarius A threading the Milky Way's destiny. Formed 12 billion years ago, its 4.3 million solar masses shaped the galaxy's heart. As 2025 ESO models confirm, early gas clouds collapsing under its pull sparked starbursts, while its flares, tracked by ALMA, enriched the core with elements for new suns. Unlike violent quasars, SGRA's modest appetite preserved the galaxy's spiral, its gravity guiding orbits like S2's without shredding the disk. This balance, powerful yet restrained, crafted a stable Milky Way, our home for 4.5 billion years. Loeb's speculation lingers. Does this precision suggest a galactic purpose? Scientists see a black hole driving evolution, but its finesse feels almost orchestrated. What lies ahead for this cosmic architect? The galactic tapestry leads us to future probes of its secrets. Sagittarius A weaves the Milky Way's tapestry, but its secrets beckon us to probe deeper. This black hole, 4.3 million times our Sun's mass, has revealed its shadow and stellar dance, yet mysteries persist. By 2025, the Event Horizon Telescope's sharper images hint at dynamic flares, but next-generation tools promise more. The Vera C. Rubin Observatory, fully operational in 2025, will scan for transient events near SGRA, catching flares or orbiting debris. Future EHT upgrades, planned for 2030, aim to resolve finer details of the accretion disk, mapping magnetic fields twisting plasma at light speed. Missions like ESA's Athena, launching in 2035, could detect X-ray bursts from infalling matter, revealing how SGRA feeds. These probes may unveil whether its quiet hunger is typical or unique. What lies beyond the event horizon, and why does this monster sleep? The cosmic frontier opens, urging us to explore its riddles. The path to Sagittarius A's secrets lies in cutting-edge eyes. By 2030, the square kilometer array's radio sensitivity could map the black hole's jets, if they exist, revealing how it shapes the galactic core. ALMA's 2025 data shows flares spiking 100 times brighter, but future scopes like the NGVLA may track their origins, gas clouds or stellar winds, down to seconds. Space-based telescopes like NASA's proposed LUVOIR could peer through dust, capturing star orbits like S2's in real time. These tools might answer why SGRA consumes so little, just 0.01% of Earth's mass yearly, compared to active galactic nuclei. Avi Loeb speculates, Could its quietude signal a cosmic purpose, a beacon timed for our era? Science leans towards sparse surroundings, but the flare's timing, aligned with our tech, intrigues. Will probes reveal a dormant giant or an active force? The cosmic riddles deepen, pushing us toward the unknown. Picture a galaxy's heart under scrutiny, its mysteries laid bare by future probes. Sagittarius A, a 12 million mile wide titan, holds clues to cosmic origins. Planned missions like ESA's LISA by 2037 could detect gravitational waves from objects merging near SGRA, revealing its past feasts. The Rubin Observatory's 2025 surveys may spot new stars or debris orbiting the black hole, hinting at its role in galactic evolution. Why does SGRA flare sporadically, unlike ravenous quasars? Is its calm a phase or a permanent trait? Loeb's voice echoes. Could its signals be deliberate, a galactic marker for advanced eyes? Scientists see a natural cycle, but the black hole's influence, shaping 400 billion stars, feels profound. As we probe deeper, will we find a sleeping monster or a key to the cosmos? The cosmic frontier leads to our final reflections. The cosmic frontier of Sagittarius A reveals a monster shaping our galaxy's heart. From its radio beacon to the frantic dance of stars, this black hole, 4.3 million times our sun's mass, bends time and space, forging the Milky Way's destiny. Its shadow, captured in 2022, and flares, seen in 2025, challenge our place in the cosmos. For more journeys into these mysteries, like and subscribe to Cosmic Depth. Is Sagittarius merely a predator, or a key to galactic secrets? As future probes delve deeper, its legacy endures, whispering of forces beyond our grasp. The galaxy's pulse calls us to keep exploring.